Alright, so here we are, back at it again. My apologies. So, here we have the parallelepiped. Again, this looks like a three-dimensional parallelogram. And what I want to do at this point in time is, in order to find the volume, what I'm going to need to do is, I need to find a base, and then I need to multiply by some height. Now, this base, it's not exactly a base like we did over here. It's actually an area that we're looking at. And that area is that area that we previously found for the area of that parallelogram. So this here is kind of deceiving when we say base, but it's more of an area. Because if we take the area and then multiply it by the height, then we add that third, my goodness, the word escapes me right now. The third unit, therefore we would get a volume. So, area of the base, we already know that. The area of the base was the area that we found previously, which was this piece. So the area of the base, that's not too bad. Now all we have to worry about is the height. What is the height of this parallelepiped? Well, again, very similar to how the height was determined in this parallelogram, we want to determine the height here of the parallelepiped, which means we have to try to determine what is the height from the bottom, or from this base area, to the very top plane here. Now, in order to do that, we then need to establish, well, somehow, some way, we need to get some added measurement in there to try to extract that height. In order to do that, we are actually going to rely on some help from the cross product. Notice the cross product of the two vectors u times v, that cross product is perpendicular to this parallelogram, or to this plane. And if we have a parallelepiped, then it will also be perpendicular to this top plane. So that is one of the items that we are going to call upon to help us. We have the cross product of u cross v. So as we start looking at the cross product for u cross v, this is now beneficial. Because at the end of the day, we also get something else for free. We get this angle, which we'll call beta. Now, if we were to determine the height of the parallelepiped based upon where w, that vector w, ends, well, that's actually going to be real nice, because we can drop, or we can add, a perpendicular to that. So now, once again, we're back into trig. How could we then try to measure a certain measurement here to grab the height for this piece here? So again, I'm not trying to find the length for w, but instead I'm trying to find this particular height. Alright, so I'm going to call that height, let's call it capital H. So this height, capital H here, the trig function that I want to use there is more than likely going to be cosine, because it's a right triangle here. So I want to use cosine of beta. This is going to be the adjacent side, which we're calling h, divided by the hypotenuse. But the hypotenuse is just the magnitude of w, which means the height can be thought of as the magnitude of w multiplied by cosine of beta. That's awesome, because over here we have the height, h. So we now coincidentally found that magnitude, or that height, for that parallelepiped, which now gets us the magnitude of u cross v multiplied by the height that we just found. What was that height? Well, that height was the magnitude of W multiplied by cosine of beta. Awesome. Look at that. Everything's right there. That is beautiful. Now, if you recall, this right here, this volume of a parallelepiped, U cross V, that's a vector. So the magnitude of one vector times the magnitude of another vector multiplied by the angle made between them. Wow. That's the definition for a dot product. This whole piece right in here. Because the definition for a dot product tells us that if we have A dot B, then we get the magnitude of A, magnitude of one vector, times the magnitude of the other vector, multiplied by the cosine of the angle made between them. And that's exactly what we have here. One magnitude of one vector times magnitude of the other vector times cosine of the angle between those two vectors. In other words, it's a dot product. So when we're looking at the volume, we're really looking at U cross V dot vector W. But this is going to produce a scalar, and scalars can be negative. So we're going to bypass that being negative because we're talking about a volume. We're going to bypass that, and we're going to make this always positive. Therefore, we can automatically conclude that this scalar triple product will produce a volume for a parallelepiped. Remember I said it was cool? There's the coolness factor. All right, so let me put pause real quick. Okay, so my apologies. I accidentally stopped the other video and it compiled when I stopped it. So this is the second portion for the completion of the dot product, or sorry, the completion of the cross product. Now, if we were asked to find whether three vectors are coplanar, meaning are three vectors on one plane, well, what would happen to this parallelepiped, or better yet, what would happen to the volume of the parallelepiped if vector W was on the same plane as vector V and U? Well, the volume wouldn't exist. In other words, the scalar triple product would condense down to 0. So, fun fact, when you're doing your homework, you will get questions that will ask you to check whether three vectors are coplanar. What are you to do? Use the scalar triple product to figure that out. And that is the cross product. I thank you all for joining me. I thank you all for putting up with my babbles and my mistake on accidentally compiling the video. But hey, we all work through it, we all make mistakes, and I hope to see you all here for the next lesson where we'll be talking about lines in R-Space 3, lines and planes. So make sure you stay tuned for that, and I will see you all next time.